Okay, so today is part 2 of organic chemistry. Okay, so part 2 of organic chemistry will focus on naming organic substances. Okay, so naming organic molecules will follow the IUPAC, the naming convention. So IUPAC stands for International Union of Pure and Applied Chemistry. So the IUPAC system is very often used for small and relatively simple organic compounds. Because the IUPAC system, right, the emphasis of this naming system is to give exact names. So which means that even if you cannot see the molecule, you can get a very good idea of, you can get a very exact idea of its structure even if you don't see the drawing. So the IUPAC is designed for very precise naming, but it's definitely not convenient. Okay, so alkanes are named with the suffix "ane". So the suffix will tell you the functional group, and the prefix actually depends on the number of carbons. So the prefix goes from 1 to 10. So prefix met, at, prop, but, pen, hex, hep, oct, non, and dec. So carbons 1 to 10. So if 1 carbon is met, 10 carbons is dec. So if you have a suffix of "ine" and "ine", right, it means that it's a alkene and alkyne. So you can have a decene and the decyne this way. Okay, and even though numbering here goes up to 10, right, if you can memorize this 10, you can actually name many different organic compounds. In fact, way beyond 10. So next slide, I'll show you how. Okay, so there are also other functional groups with different suffixes. So alcohol is "ol", thiol is a thiol, aldehyde is a "al" suffix, ketone will be "one". Okay, carboxylic acid, whether it's a oic or OAte, okay, depends on whether it's a acid or the conjugate base is present. So again, the properties are different and therefore there are slightly different names. So acetic chloride is a OL chloride, amine is amine, amine. Okay, so if you have palmitic acid, so palmitic acid is actually the common name for a saturated fatty acid with 16 carbons. So how would we name 16 carbons? Okay, how I like to describe this student is 16. So it's a combination of the words 6 and 10. So 6 and 10. So to name 16 carbons, right, it will be hex and then followed by dec. So it's hexadecanoic acid because it's a fatty acid, it's a carboxylic acid. So it's a hexadecanoic acid. So you can easily name substances up to 20 carbons. Okay, so or even above, beyond 20 carbons. So if hexadecanoic acid is 16 carbons, right, if for 20 carbons it will be, it's somewhat similar to dec, but for 20 carbons it's actually simply dodec. So dodecanoic acid, if it's a dodecanoic acid, means there's 20 carbons. So you can see, even with the 10 prefixes, right, it can allow you to name even beyond 20 carbons. Okay, and as molecules get larger, it becomes more and more important to assign a number to indicate the position of the functional group. Because remember, the molecules actually have a shape, and the position of functional groups will alter the shape of the molecule by a lot, and it also will affect how the functional group will interact with other reagents. So position and shape is very important. Okay, so when it comes to numbering, functional groups are always assigned the smallest possible number. So that's why in this example here it's 1 chlorobutane instead of 4 chlorobutane, because you start counting here to give the Cl the smallest possible number. Okay, and different functional groups can also be numbered, like this is 3-pentanol, 3-pentanone, and 3-pentanethiol. So you can put 3-pentanol at, okay, there are some books that go penta-3-ol, which is the same thing. So both are acceptable. Okay, and in many molecules, right, it's very important to identify the parent chain. So when you name right, you start naming from the parent chain here. So the parent chain is basically the longest chain. So anything that's not part of the parent chain, right, is considered a substituent group. So anything that's not part, it can be a methyl, ethyl, or propyl. Okay, and there are also some special functional substituent groups like isopropyl. Okay, this is a CH3 substituent. This is a CH2-CH3 substituent. This is a CH2-CH2-CH3 substituent. Okay, so this is 1 carbon, 2 carbon, 3 carbons. And isopropyl. Okay, isopropyl also have 3 carbons. Main difference is that when it's connected to the parent chain, right, it's connected in the middle carbon instead of one of the side carbons. So isopropyl is just that propyl connected in the middle carbon. Okay, so this one is 1, 2, 3, 4, 5. So this one is a pentane. So when you count the parent chain, you name the parent chain first. This is 1, 2, 3, 4, 5, 6, 7. So this is a heptane. So this is a methyl and it's on the second carbon. So it's 2-methyl. This is ethyl and it's on the fourth carbon. So this is 4-ethyl heptane. So that's how it works. Okay, so quite often people will actually draw the parent chain horizontally this way, quite often. But don't immediately assume that just because it's drawn horizontally, right, it is the parent chain, because this is not a rule. Okay, so like for this one, the parent chain is drawn vertically, 1, 2, 3, 4. So this one is not 1, 2, 3. So it is 2-methylbutane and not 2-ethyl propane. So you go for the longest possible chain, and anything that's not a part of parent chain is the substituent group. Okay, cyclic structures. Okay, cyclic structures, the rule for parent chain is a little bit altered, but it's also much simpler. If you have a cyclic structure, right, the cyclic structure itself is the parent chain, so it's much simpler. So you can have cyclopropane, cyclobutane, cyclopentane, or cyclohexane. So cyclopropane and cyclobutane, if you notice, you don't see this kind of structures very often. Okay, they exist, but they are also quite unstable because carbon is usually tetrahedral, and tetrahedral, the shape is 109 degrees. So a triangle is very, very different from 109 degrees. A square is also very different from 109 degrees. This one, a pentagon. Okay, a pentagon is not very stable, but it's close enough to 109 degrees. And this one is a hexagon. So hexagon is very, very close to 109. So this is the most stable, followed by this one. So pentane and hexane, quite common. Butane and propane, not very common because it's very far from the ideal bond angle of carbon. So these are not very common. Okay, and when you have multiple of the same substituent, like you have multiple methyls or multiple fluorines, you use di, tri, and tetra. So again, you still assign the thing to the smallest possible number. Like this one, 1, 2, 3, 4, 5, 6. So this is a hexane. Substituent group methyl, methyl. So this is 2,5-dimethyl hexane. This is 1, 2, 3, 4, 5. So 5 carbons. So this one, 1, 2, 3. So this is a trifluoro. So it's a 1, 2, 2 trifluoropentane. Okay, and for this structure in particular, note that the fluorine here is on the same sort of line as the carbon, right? Okay, so be careful not to count the fluorine as a extra carbon, because sometimes people go 1, 2, 3, 4, 5, 6, counting the fluorine as extra carbon. So this one, be careful of it. Okay, ethers and sulfides. Okay, so these two functional groups, right, because they have a break in the chain, So the important thing to note that being a chain, right, is that you name the functioning the groups on either side of the chain. So this is a ethyl, this is a ethyl. So that means this one is diethyl ether, this one is a ethyl methyl ether, and this one is a dimethyl sulfide. Okay, so what this tells us is that if you want to determine a parent chain, right, you cannot count past the oxygen like that. So this one causes a break. And if you want to know which is the parent chain actually, right, in ethyl or sulfide, right, depends on which side has the longer chain, but you cannot count past the oxygen because it causes a break in the chain. Okay, and for esters, okay, in esters, the group which is attached to the oxygen, which is the alcohol group, the alcohol group is named first. So this one is from ethanol, so this is ethyl, and this one is from propanoic acid, this group here, so this one is ethyl propanoate. Okay, so if an amide is unsubstituted, the suffix is simply amide. So like this one is a 1,2,3 propan amide, straightforward. But if the amide is substituted, you have to name the substituent group. So this one is N-propan amide, and you notice here there's an N, right? Okay, because for carbon you can use a number, but for nitrogen, right, nitrogen is not a carbon, so you don't use a number. So the N here shows that the methyl group is attached to the nitrogen of the amide, so that's why it's N. Okay, so what is the name of this molecule? So you can get molecules that look very, very odd, just like this, but again the rule is still the same. You find the parent chain, so 1 2 3 4 5 6 7, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7 8 9. Okay, so this is 9 carbons long, so this is a nonane. And then in terms of this is a methyl, this is a methyl, so it's a dimethyl, and this is a ethyl. 1 2 3 4, so this is a 3 4 dimethyl 4 ethyl nonane. Okay, so there are actually many more rules in the IUPAC system, and if you notice like many rules in chemistry, right, the IUPAC system actually has many layers. So these are just the first few layers. And IUPAC naming for larger molecules, they actually have special rules for larger molecules, but IUPAC naming in general can get a little bit unpractical for larger molecules. So this example here is to illustrate. So this is a flavonoid. Okay, and this one is a 3-ring structure, right? So this is a parent chain. Okay, and this one is not just a simple ring, so you don't call it cyclo or benzene or anything. So this is a 3-ring structure. This is a very special parent chain. So this 3-ring structure here is called a flavone. So this 3-ring structure here is called a flavone. So this is one of the special rules. And there are 1 2 3 4 5 different hydroxy. So this is a pentahydroxyflavone. So the numbering here, right, is also based on this parent chain. So IUPAC also specifies how you number the carbons in this special chain. And this one is a glucose, that's why it's 3-beta-glucoside. So special suffixes, flavones and glucoside. This is basically a glucose. So using IUPAC name, right, it's actually a very long name. In fact, if you were to buy this chemical from a vendor, right, you say, can you sell me this compound? 3 prime 4 prime 5 7 pentahydroxyflavone 3-beta-glucoside. The vendor probably get very confused and then wouldn't know what to sell you. So instead, usually we will call this by its common name. So the common name for this is quercetin 3-glucoside. So 3 meaning that the glucose is attached to the third carbon of quercetin. So you are not required to know this, because the only people who would actually want to know this name, right, are people who are doing their PhDs on flavonoids. Then yes, you might actually want to know how to name these names. But this is a case of there are many different special rules in IUPAC, many layers. So for first year chemistry, right, you are not required to know this. This is just to illustrate. Okay, so now we go a little bit into organic reactions. So most organic reactions occur because nucleophiles will interact with electrophiles. So nucleophile is something that donates a electron pair. So usually a nucleophile is something with a free electron pair or at least one double bond. So this allows them to have extra electrons that they can donate. So they are by definition Lewis bases. So this one they use the Lewis definition of the acids and bases. Okay, an electrophile in contrast is a Lewis actrate. So they are attracted to electrons and can accept an electron pair. So they are usually positively charged or have a partial positively charged, but not always. But they also usually have a free orbital which can interact with the extra pair of electrons. Okay, so basically how you donate electron pair is that electron pair gets donated and it forms a new bond. Okay, so there are a few types of organic reactions. The first of which is addition. So addition is when an atom or group of atoms is added to a molecule without the removal of any other atoms. That means you just add something and you don't remove anything. So alkenes will undergo addition with halogens. So a very similar reaction is used to add hydrogen to unsaturated oils to create margarine. So use a transition metal catalyst such as nickel to add hydrogens to unsaturated oils to create margarine. Okay, so this is a very common experiment in the lab. So in the lab, bromine is often a brown liquid. So it can interact with double bonds. So once bromine reacts with double bonds, right, you get a haloalkane. So in this case, a dibromoethane. So this is brown in color, but this is colorless. So this reaction will actually cause the bromine to be decolorized. Alkenes can also undergo addition with hydrogen halides. Okay, but unlike halogens, right, hydrogen halides, hydrogen and a halogen. Okay, this is not a symmetrical reagent because one is a H, one is a halogen. So this will cause asymmetric alkenes, and when it's a symmetric alkene, right, it can result in two possible products. Okay, so to know which of the two possible products is your major product, right, you will use Markovnikov's rule. So it applies favoring the addition of the acidic hydrogen to the carbon with more hydrogen. So Markovnikov's rule states that for addition, right, you add hydrogen to the carbon with more hydrogen. Okay, another way to describe this rule is that CH3 is more stable than CH2, more stable than CH. So when you add it to something with more hydrogen, right, you're more likely to get CH3. So that's why Markovnikov can be stated that way as well. So CH3 more stable than CH2, more stable than CH. Okay, so example here. So this is a alkane. This is a alkene. This is a halogen, HCl. And this is a hydrogen halide. Okay, so hydrogen can be added to this carbon or this carbon. Okay, so which is the major compound, A or B? So this is a CH2, this is a CH. So CH2 has more H. So H will more likely be added here. So if H is added here, Cl is added to the other carbon. So B is the major product. A is also produced but in smaller quantities. So B is the major product. Okay, and one important thing to note Remember the rule that in a reaction, right, maximum only two molecules can interact. So in this case, it's this alkene and this hydrogen halide. So only two molecules can interact in a reaction. So that means it's only between one molecule and one molecule, two molecules. So that's why you will never get things like ClCl, because that would require three molecules. So you can only get one of these two. Okay, so for this one, if you add HCl to this substance here, we will give you more of this or more of this. So that means the question is also whether H will be added here or here. Okay, so this is a little bit of a funny situation because this carbon here is a CH. This is also a CH. So they have equal number of hydrogens. So in such a case, right, you will get 50% of this, 50% of this in equal amounts because they both have the same number of hydrogens. Okay, and carbonyl groups can also undergo addition. In fact, when you dissolve a ketone in water, it automatically forms a hydrate. That means you have a ketone in reacts with water, it forms a diol this way. That means OH on the same carbon. So this is very polar. So which is why acetone, for instance, is actually very miscible with water. It's very miscible with water. So acetone itself will not be very polar. But because of this equilibrium, right, this group here is very polar. So which is why acetone is freely miscible in water because of this equilibrium. But of course, this is not a permanent addition, and in fact, this form here is more stable. So if you were to distill out the ketone, right, it will return to this form. So it's not a permanent addition, it's an equilibrium. Okay, so if you want to do a more permanent addition to a carbonyl group, you need what is called a Grignard reagent. So Grignard reagent is basically an alkyl, that means a organic substance bonded to Mg and Br. So this is a Grignard reagent. So basically the Grignard reagent will actually attack the carbonyl. It will attack the carbonyl and attach the drawing here. The alkyl group here. So you will get you will actually get this product here because the blue group is attached to the carbonyl. And when the carbonyl completes the reaction, right, it becomes a OH. Okay, so tricky thing about this is that you have to practice drawing the product. Okay, and even in cases where you don't actually have to draw the product, right, even in questions where you don't actually have to draw the product, drawing the product helps you imagine. It helps improve your imagination, so that if you're given multiple options that all look sort of correct, right, if you're able to draw the product, right, you can better identify which structure is the correct structure. So it is definitely helpful to really practice how to draw. And one thing about drawing, like, even though this drawing here forms like a cross, right, it's actually not very good practice to actually draw a straight line like this, because here I can't really see the angles very clearly. So try not to draw it like a cross like this way, because the angles will tell me the number of carbons. So if you draw a straight line like this, it's no longer an angle, right? It's actually a little bit difficult to tell how many carbons it is. And this is still quite neat. If you're drawing with a pen and paper, right, definitely very difficult to see number of carbons. So I need to be able to count the number of carbons to know the structure is correct. Okay, so Grignard reagents are actually a very significant discovery. So it's actually, they were first created by this French chemist, Francois Auguste Victor Grignard. So he was awarded the Nobel Prize in Chemistry in 1912. So he was awarded this Nobel Prize because this is actually a very significant discovery. And if you notice, right, the new bond formed here is between a carbon and carbon bond. So it's one of the few reactions that can form a carbon and carbon bond, and that's why it's very important in many organic reactions to create organic new organic compounds or organic synthesis. So that's why it's one of the few reactions that can create a carbon-carbon bond. Okay, and why this is so challenging? Carbon-carbon bonds are very stable, and this means that carbon-carbon bonds are very difficult to break. But similarly, if carbon-carbon bonds are very difficult to break, they are also very difficult to form because the bond energy is actually quite high. Okay, so to test whether you can actually imagine or draw this reaction properly. Okay, what product would this Grignard reagent form when it reacts with acetone? So this is a ethyl, this is a MgBr. So this one you try to draw on your own and see, because I didn't actually prepare the drawing, but this one shouldn't be very hard. Just try to draw this on your own. Okay, another one. Oops, oh no, sorry, I did prepare the drawing, I forgot. Okay, so this is the answer. Okay, so remember, this is 1, 2, 3 carbons. This is also 1, 2, 3 carbons. This 1, 2, 3 carbons. So this is from the acetone group, and after it's reacted, it becomes a OH. Okay, ethyl. So this is Grignard reagent bond to the carbonyl carbon. So this is a ethyl group bonded. So this whole structure, right, is 2-methyl 2-butanol. So it works this way. Okay, so if you can't really get this in your drawing, right, it means you need a little bit more practice. It can be a little bit challenging to actually imagine the 3D shapes of these molecules. Okay, and one more, drawing this one. What would happen if this were to react with carbon dioxide? Okay, carbon dioxide is a carbonyl, as carbonyl here, so it does react with a Grignard reagent, ethyl MgBr. Okay, so what would happen? Okay, the product that's formed would actually be propanoic acid, because this is ethyl and this is extra carbon, so it becomes 3 carbons, so it becomes a prop. And because if it reacts with a carbonyl group, right, it becomes a OH. So carbonyl with OH, it becomes a carboxylic acid, so it becomes propanoic acid. Okay, and when it becomes propanoic acid, right, it is no longer a carbonyl group because it has become a carboxyl group. So Grignard reagents cannot react with carboxyl groups, can only react with carbonyl groups. So that's why it becomes propanoic acid. Okay, so with this, okay, that's the end of the second part.